Hello, I'm Behnaz Hassan Shahi. Today I'm going to present our work Gelato, which is a dynamic web application security testing tool. This is a joint work with Hyunjin Lee and Paddy Krishnan from Oracle Labs, Australia. In the past 2 decades, many tools and techniques have been proposed to detect vulnerabilities in web applications, and the question is whether they are good enough for our modern web applications. Most of the techniques either focus on the test input generation and crawling aspect or the security analysis, and they do not, for example, direct the crawling for more efficient security analysis. Also, the proposed security analysis for JavaScript are oftentimes very heavy, and they do not scale well to the complex applications that we use these days. These applications usually have different types of inputs, events, and input values, and the tools do not support all these types of inputs at the same time. And also, our modern applications are using complex frameworks such as React and AngularJS, but unfortunately the existing tools are not designed to perform well on these frameworks. Gelato makes various contributions. First, by combining static and dynamic analysis, we improve the performance and coverage of security analysis. We propose a feedback-driven approach that makes us able to analyze modern framework-based JavaScript applications. We also propose a novel staged change analysis that is lightweight and is not intrusive and fits well into our crawler. And also we have a component that generates input values and also events to generate inputs for modern web applications more effectively. At a high level, you can think of Gelato as a tool that mimics an attacker. It has full access to the client side, but it has a black box view of the server side. By interacting with the client side, it tries to find ways to penetrate the application. Gelato both finds vulnerabilities on the client side, and also by detecting entry points to the server side, it allows finding vulnerabilities on the server side. The users of Gelato only need to provide a URL, and then Gelato will go to the state, the relevant state for that URL, and it fetches the JavaScript code that is returned from the server side and runs a call graph analysis to generate the call graph. This analysis is static, and the static analysis of JavaScript is known to have challenges. It can have both a low precision and also miss, for example, edges in a call graph. So we propose a feedback-driven approach that refines the call graph at runtime. Using the call graph, we compute metrics that help us to prioritize the crawler. For example, by computing the distance from an entry point to a security-sensitive point, we choose an event that is closer to a security-sensitive point. We provide various guiding strategies based on the static call graph to do the prioritization. But also, in one of our strategies, we use random, basically, event selection to avoid getting stuck in local optimums in the search space. To give an idea how the call graph refinement works, on the right-hand side, there is a very simple HTML code where there are two buttons, button 1 and button add 1 and button add 2. When we click on these buttons, the handle click function would be called, which at line 2 calls fn.call, and this call resolves into the target function at line 1, which calls the fetch API that is going to send a request to the server side. The fetch API for us is a security sensitive API. When the static call graph analysis wants to generate a call graph, it is not able to resolve the call from fn.call to the target function. However, we do not stop, and Gelato randomly clicks on one of the buttons anyway. So by clicking on button 1, for example, it is able to generate the execution trace, which shows that the fn.call is calling the target function, is resolving the target function. So we add that missing edge to the call graph, and next time when Gelato wants basically to decide whether to click on button add to or not, it is going to click on it because it knows that it's going to reach the fetch function at line 1. We have a component that generates input values, which are quite important when it comes to complex JavaScript applications. By collecting constraints for certain operations, for example, string concatenation that are tainted, we generate inputs that bypass those constraints to improve coverage. We also have a taint analysis that is quite lightweight and is designed to scale and be practically useful for modern web applications. We perform the staged analysis once a new state is basically generated in the browser. And also we use the taint analysis when we are trying to collect the constraints for input value generator to only collect constraints for the relevant operations. We prioritize the crawler to more quickly reach the security sensitive points, for example, DOM operations when we are trying to detect DOM-based XSS vulnerabilities as well. Most of the proposed techniques for performing taint analysis on JavaScript application that are dynamic are using a technique called taint tracking, which relies on propagating taints as the application runs. There are two main limitations with these taint tracking approaches. First, the taint value can get lost when it enters the external code, and second, because the taint propagation needs modifications to either the source code or the basically browser engine, it is very easy to break the semantic of the program. Instead, we propose a taint inference approach where the basic idea is that we compare the values at sources and sinks. So we have 4 stages. At the first stage, if the value at the sink is a subset of is a substring of the source, we report that as a potential taint flow. If not, we compute the edit distance between the 2 values, and if it's below a threshold, then we perform the third check, which mutates the value at the source, and we observe whether the value at the sink has changed or not. If that's true, then we perform the final check by counting the string operations and see whether they match the edit distance operations. These extra stages help us to avoid false positives in detecting taint flows. We have evaluated Gelato on various applications that use frameworks such as React, AngularJS. We also have made sure to have both multi-page applications and single-page applications, because we have observed that in the literature, oftentimes tools are just evaluated on more traditional multi-page applications, which are not representative of the apps we use these days. 3 of the applications are anonymized because they are used internally at Oracle. Compared to the existing tools, Gelato can detect more URLs and trigger more REST endpoints on these applications. In particular, crawljax, which is actively used in the ZAP penetration testing tool, is not performing as well as Gelato, which is showing the effectiveness of our tool in terms of coverage. To understand the different strategies that we use for guiding our crawler, we have chosen four strategies. The first one is purely random, that selects the next event randomly. The second one is called assisted ACG, where we provide models, manually crafted models for the call graph when it is not able to detect edges. And the third one is a feedback-driven approach where we refine the call graph fully automatically at runtime. And the fourth one is the composite approach, which combines all the previous ones. Overall, the random strategy is not performing as well as the call graph-based strategies, but these strategies also have very different effects on different applications. The good news, however, is that the feedback-driven approach, which is uses the hybrid analysis, is performing competitively with the assisted ACG, which is using manual models, and that's a good news that combining static and dynamic analysis can be effective for complex JavaScript applications. To evaluate the effectiveness of our taint analysis, we have compared Gelato with two state-of-the-art taint tracking tools, Dexter.js, which propagates taints by instrumenting the source code, and Chromium Taint Tracker, which instruments the Chromium engine to propagate taints. We have evaluated these tools on libraries and applications with known DOM-based XSS vulnerabilities. And as you can see, Gelato is the only tool that can detect all of these vulnerabilities. To understand whether Gelato has high precision or not, because we are using taint inference instead of taint tracking, we have compared it on two micro benchmarks, firing range from Google and IBM benchmark, and as you can see, compared to the other tools, Gelato has better precision and recall, which shows the effectiveness of our tool. In conclusion, thanks to the feedback-driven design of Gelato, we are able to perform crawling with better coverage and performance, and our tool outperforms these existing crawlers on modern framework-based applications. Moreover, our explorations show that guiding a dynamic analysis with a lightweight static analysis for JavaScript applications is promising. And also we propose a novel lightweight taint analysis for JavaScript that has better precision and recall compared to the state-of-the-art tools. It is not intrusive, and also it is able to handle built-in libraries. Gelato is actively used at Oracle these days, and it's and is making great impact. Thank you.